Think about this. We have these incredibly powerful artificial intelligence models, but their knowledge often resides in many different places.
Right, like spread out.
Yeah, it could be data spread across individual smartphones or, locked within the private servers of various organizations.
Uh,
The big puzzle is how we efficiently update these massive AI brains with all that scattered information without compromising anyone's privacy.
it's a huge challenge.
It's like trying to coordinate a huge group project where everyone has valuable pieces of the puzzle, but, well, nobody can directly share their individual parts.
That perfectly describes the challenge that federated learning aims to solve. Instead of pooling all the raw data in one central location, federated learning brings the training process to the data itself.
Okay.
Each device or organization trains the AI model locally using their own information, and then only the learning outcomes the model updates are shared and combined.
So the sensitive raw data stays put.
Exactly, maintaining privacy.
So we're essentially learning together while keeping our data separate. That sounds like a great step for privacy. Now, these foundation models, the really large AI models, they can have billions of parameters.
Billions, yes.
Even making small adjustments, what's called fine-tuning, that can be very demanding in terms of computing resources.
Immensely.
This is where parameter-efficient fine-tuning, or PEFT techniques, come into play. Imagine it as tweaking just a few key settings on a complex machine to get the desired result, rather than having to recalibrate the entire system.
Exactly. And a particularly popular PEFT method is low-rank adaptation, often referred to as LoRA.
LoRA, right.
The fundamental idea behind LoRA is that the changes needed to adapt a pre-trained model for a specific task often lie within a lower dimensional space.
Okay, simpler somehow.
Kinda.
Yeah.
So instead of altering all the original parameters, LoRA introduces small, low-rank matrices to certain layers of the model, and only these smaller matrices are trained. This significantly reduces the computational cost.
Fewer settings to adjust, got it. Now, when we combine federated learning with LoRA, we get federated fine-tuning using LoRA. It sounds like a very efficient approach on the surface.
It does.
However, this deep dive is focusing on a potential bottleneck within this combination, right?
Wow.
What's the core issue we're exploring?
Well, the research we're looking at points out that simply averaging the LoRa updates from different clients, which is a common practice, isn't actually the most effective way to combine the learning.
Oh,
Ideally, the aggregated update should be the average of all the individual client updates considered together. But this ideal combined update often doesn't fit within the low-rank constraints that LoRa imposes.
okay, so the average of the individual small adjustments might not be the same as the single best small adjustment we could have made if we saw all the data together.
It's a good way to put it.
It's like if multiple cooks each slightly adjust a recipe, the combined result might be more than just the sum of those individual tweaks.
Precisely. Now, there are existing methods like FedEx LoRa and Flora that try to achieve this exact aggregation.
Right.
Right. However, they often lead to a substantial increase in communication costs. The amount of information that needs to be sent back to the central server for aggregation can increase directly with the number of participants.
Ah. Oh.
Imagine each cook needing to send detailed reports on their every tiny ingredient change, and this volume grows with each additional cook. This can quickly become impractical.
So we improve the accuracy of the update, but we run into a problem with the amount of data that needs to be transferred, like having a perfect recipe that requires just too many ingredient deliveries.
Exactly that. And then we have other methods that aim to reduce communication, like FFA LoRa.
Okay, the flip side?
But these often compromise the model's ability to learn effectively by limiting its expressiveness, for example, by keeping some parts of the LoRa adapters fixed.
Ah, so a trade-off.
It's a trade-off, less communication, but the final result might not be as good. Furthermore, when we're dealing with privacy-preserving federated learning.
Right, adding noise.
Yes, where we add a controlled amount of noise using a technique called differential privacy to protect individual data, using standard LoRa can actually amplify this noise.
Amplify it. That sounds bad.
It is. It further degrades the model's performance.
Noise amplification sounds detrimental. It's like trying to add a little bit of seasoning for privacy, but accidentally overpowering the whole dish.
That's a perfect analogy. This leads us to the central focus of our deep dive, a new research paper that introduces federated silver bullet, or Fed-SB.
Federated.
This novel approach builds upon a recent advancement in low-rank adaptation called LoRa-SB.
Federated Silver Bullet, that's a confident name. So what's the specific problem that FedSB aims to address? Let's dig into the paper's points.
Okay, so the paper really pinpoints several key challenges. Firstly, as we've just discussed, the standard federated averaging of low-rank adaptation LoRa adapters results in suboptimal updates.
Right, the averaging issue.
Yeah, because the ideal aggregated update often goes beyond the inherent low-rank nature of LoRa. Think back to our cooks. Adjusting the recipe, simply averaging their individual small changes, might not yield the best small change for the overall recipe.
Right, the combination might require a slightly different kind of
Yeah.
adjustment. And what about the existing solutions for this? You mentioned FedEx LoRa and Flora.
Exactly. These existing solutions that aim for exact aggregation, like FedEx, LoRa, and Flora, they solve this aggregation issue, but, and it's a big but, at the cost of significantly increased communication. The amount of data that needs to be exchanged scales linearly with the number of participating clients. That creates a communication bottleneck as the number of collaborators grows.
So better updates, but it becomes less practical with more participants. What about methods that try to reduce this communication overhead, like FFA LoRa?
Well, methods like FFA LoRa that try to reduce communication often sacrifice the model's performance. By keeping certain parts of the LoRa adapters fixed, they limit the model's ability to learn the best adaptations for each client's unique data.
It's like telling our cooks they can only adjust one specific ingredient, even if tweaking others would lead to a better overall flavor.
Precisely. And then there are the added challenges in privacy-preserving federated learning.
Which you mentioned earlier, the noise amplification.
Right. In privacy-preserving FL, applying differential privacy to standard LoRa can amplify the noise added for privacy protection. The paper explains that this noise amplification occurs due to the interaction of the noisy low-rank adapter matrices, leading to a degradation in model performance.
Okay, so we have suboptimal aggregation, high communication costs for accurate aggregation, performance trade-offs for low communication, and noise amplification in private settings. That really sets the stage for what FedSB is trying to improve. So what is the federated silver bullet approach? How does it actually work?
Okay, so Federated Silver Bullet, or FedSB, is the federated version of a technique called LoRa-SB.
LoRa-SB silver bullet.
Yeah, low-rank adaptation with a silver bullet initialization. To understand FedSB, we first need to quickly grasp LoRa-SB in a non-federated setting. LoRa-SB learns a small square matrix, I call it R in the paper, that sits between two fixed low-rank adapter matrices named B and A.
Fixed, so B and A don't get trained.
Correct. The crucial idea here is that by specifically learning this intermediate R matrix, LoRa-SB can more effectively align its learning process with what a full fine-tuning of the entire model would ideally achieve within that low-rank space.
So instead of learning the B and A matrices directly, LoRa-SB keeps them constant and focuses on learning this connecting R matrix. What's the advantage of that?
Well, this design significantly reduces the number of parameters that need to be trained. But more importantly, it allows for better model updates because of the specific way the B&A matrices are initialized in LoRa-SB.
Ah, the initialization matters.
Yes, this initialization helps LoRa-SB more accurately approximate the results of a full fine-tuning, something that standard LoRa methods often struggle to do with the same number of parameters.
Okay, so LoRa-SB is already a more efficient fine-tuning method in a centralized setting. Now, how does FedSB bring this efficiency to the federated learning context?
Okay, so in FedSB, the central server takes these fixed adapter matrices, B and A, from LoRa-SSB and distributes them to all the participating clients.
Got it. Sends them out once.
Exactly. The key is that each client then only trains that small square R matrix using their own local data.
Ah,
All the clients receive the same B and A matrices, but they each learn a different R matrix that's tailored to their specific data set.
I see. So the potentially large B and A matrices are shared just once, and then each client focuses on training this much smaller R matrix.
Yeah.
That sounds like it could save a lot on communication.
A huge amount. And this leads to the elegant part for aggregation. When it's time to combine the learning from all the clients,
Yeah.
the central server simply averages the small R matrices it receives from each of them.
Just averaging the R matrices, how does that result in a meaningful global update for the model? That sounds almost too simple.
It does, but it works because the update performed by each client is essentially the product of B, their locally trained R matrix, let's call it RI, and A, so BRIA. And because matrix multiplication distributes over addition, averaging the individual Rye matrices and then multiplying by BNA is mathematically equivalent to averaging the full low rank updates, BRIA, that each client would ideally contribute.
Wow.
This guarantees an exact aggregation of the learning, and the beauty is that the communication cost with the client sent to the server is just the small R matrix. Its size is independent of the number of clients.
That's really clever.
Mm.
By fixing BNA and only training R, they've created a communication-efficient method that still achieves an optimal combination of the local learning.
Yes.
It's like our cooks all start with the same base ingredients, BNA, and then each sends back just a small note about their specific adjustment R, and the head chef can simply average those notes to get the overall adjustment for the master recipe.
Precisely. That's a great way to think about it. Now, to see how well this federated silver bullet approach performs in practice, the authors conducted a comprehensive series of experiments.
Let's hear about them. Tell us about their experimental setup. What kind of tasks and models did they use?
Sure. They evaluated FedSB across 3 different types of natural language processing NLP tasks. These included common sense reasoning, arithmetic reasoning, and language inference. Pretty diverse set.
Okay.
And to ensure the robustness of their findings, they tested FedSB on a variety of large language models, LLMs, the big ones like Mistral 7B, Gemma 2.9b, and Llama 3.23b, but also a smaller model, BERT-based.
It's covering different scales.
Exactly. This range of models helps demonstrate the general applicability of FedSB.
And how do they simulate the federated learning environment itself?
For the federated learning part, they distributed the training data across a simulated group of clients, basically following standard practices used in this area of research. They also considered both scenarios, where privacy is a concern and where it isn't.
Important distinction.
Very. For the privacy-sensitive scenarios, they used differential privacy implemented through DPSGD, which stands for Differentially Private Stochastic Gradient Descent.
DPSGD, right.
This technique adds carefully calibrated noise to the training process to protect the privacy of the individual data points.
So they weren't just looking at performance in an ideal setting, but also how it holds up when privacy safeguards are in place. Yeah. And who did they compare FedSB against? The competition.
They benchmarked FedSB against several state-of-the-art federated fine-tuning methods. The list included FEDIT, FedEx LoRA, FLORA, and FA LoRA.
The ones we discussed earlier with their drawbacks.
Exactly. This direct comparison allows us to see how FedSB stands relative to the current best approaches in the field.
And what were the key results? Did FedSB, live up to its silver bullet name?
The results were quite impressive, actually. The paper reports that FedSB consistently outperformed the other methods in terms of accuracy across all the models and the different NLP tasks they evaluated.
Outperformed
And it achieved this while significantly reducing the amount of communication required, in some cases by up to 230 times compared to the other state-of-the-art techniques.
230 times.
Oh.
Wow.
Yeah, it's a huge number. The authors included a figure 1 in their paper, which visually illustrates this. It shows FedSB achieving a better balance between performance and communication costs than previous methods. They call it establishing a new Pareto frontier.
A 230-fold reduction in communication costs is massive. Can you give some specific examples of these improvements from their findings?
Certainly. For instance, for common sense reasoning using the Llama 3.23b model, FedSB achieved a higher accuracy than FedS while requiring 6 times less communication.
6 times less than FedS.
And it also outperformed FedEx LoRA and FLORA with 31 times lower communication costs. That's detailed in their table, too.
31 times less than the exact aggregation methods. Significant.
Very. And in the case of arithmetic reasoning with the Mistral 7B and Gemma 2.9b models, the reductions in communication cost were even more substantial. For example, on the GSM-8K benchmark with Mistral 7B, FedSB showed up to 234 times lower communication compared to FedEx LoRA and FLORA.
234x.
All while either improving or maintaining the same level of accuracy. Figures 3A and 3B in the paper provide a good visual representation of these comparisons.
Think about what that means in practice. A collaborative AI project with hundreds, even thousands of participants could function without being totally bottlenecked by data transfer speeds.
Exactly. It really opens up possibilities.
Those are compelling numbers.
Yeah.
What about the results in the privacy-preserving settings? How did FedSB perform when differential privacy was applied? Did the noise cause problems?
That's another strong point for FedSB. In the experiments involving private federated fine-tuning of the BERT-based model on the SNLI dataset, FedSB consistently outperformed the baseline methods across various levels of privacy protection.
So even with added noise.
Even with added noise, and this was achieved while also using fewer trainable and communicated parameters. You can see this in Table 5 and Figures 4b and 6 of the paper.
So it's not just more efficient and performs better generally, but it also seems to handle the added complexities of privacy constraints more effectively. Why is that the case? What's the mechanism?
The authors explain that FedSB avoids the noise amplification issues that can affect other LoRa-based methods in private settings.
Oh.
It's because only the small R matrix is being trained, and the update process remains linear. There's less opportunity for the noise to interact and grow. Furthermore, because FedSB inherently has fewer trainable parameters compared to standard LoRa.
Just the R matrix.
Right. The amount of noise that needs to be added to achieve the same level of differential privacy is lower. Less noise needed means better performance under those privacy constraints.
Huh. That makes sense.
They even include a mathematical proof, Lemma 1, to support this, basically showing that a smaller number of trainable parameters generally leads to better privacy guarantees for a given amount of added noise.
Okay, that makes intuitive sense. Fewer parameters to add noise to, and a more direct update process helps prevent that noise from compounding. Based on these results, what are the main conclusions the authors draw from their research? What's the takeaway?
The primary conclusion is that FedSB offers a highly efficient and scalable solution for federated fine-tuning of large language models, both in private and non-private settings. It achieves accurate and optimal aggregation by simply averaging those small R matrices.
Keeping communication low.
Exactly. Keeping communication costs low and, importantly, independent of the number of participating clients. This is a significant advantage over previous exact aggregation methods where communication scaled with the number of clients.
Right, that linear scaling was a killer.
It was. So overall, FedSB effectively balances model performance and communication efficiency, surpassing the limitations of earlier LoRa-based federated fine-tuning approaches. And they really emphasize that FedSB is particularly well-suited for privacy-preserving federated learning due to its reduced noise amplification and fewer trainable parameters.
It sounds like they've indeed found a way to address many of the key challenges in federated fine-tuning. What were some of the novel contributions, data sets, and benchmarks introduced or significantly utilized in this work? What's really new here?
Well, the most significant novel contribution is the introduction of FedSB itself, obviously. It's a new federated fine-tuning method based on the principles of LoRa-SB. The paper clearly demonstrates the novel approach of achieving exact and optimal aggregation through the simple averaging of the R matrix that's a key advancement.
That aggregation technique seems central.
It really is. The substantial reduction in communication costs compared to existing methods is another major contribution. And furthermore, the demonstrated improvement in performance within privacy-preserving federated learning, attributed to mitigating noise amplification and reducing trainable parameters, is also a notable contribution.
And what about the data and evaluation side? Any new benchmarks?
They conducted extensive evaluations across a diverse range of existing, well-established NLT benchmarks. For common sense reasoning, they used Common Sense 170K, which is actually an aggregation of 8 different established common sense reasoning datasets.
Okay, comprehensive.
For arithmetic reasoning, they utilized the GSM-8K and math datasets. And for evaluating performance in private federated learning, they used the SNLI dataset for natural language inference. Importantly, they applied their method to state-of-the-art large language models like Mistral 7b, Gemma 2.9b, and Llama 3.23b within the federated learning framework, which really showcases its relevance to current AI.
It's definitely valuable to see it tested across such a variety of tasks and modern models. It certainly strengthens the credibility of the findings. Now, based on the paper, can we sort of infer what the author's thought process might have been in developing FedSB? How did they get here?
Well, reading between the lines and looking at how they frame the problem, it seems the authors began by identifying the clear limitations of existing federated learning techniques, particularly when combined with LoRa.
The trade-offs we discussed.
Exactly. They likely recognize that inherent trade-off between the accuracy of model aggregation and the communication overhead involved. They also probably observed the challenges that arise in privacy-preserving settings due to noise amplification in standard LoRa.
Okay, problem identified.
Then, given the demonstrated effectiveness of LoRa-SB in centralized learning, that specific way it uses the R matrix, they likely hypothesized that adapting its core principles to the federated setting could be the key.
The R matrix again?
Specifically, training only the small R matrix locally and averaging it globally. They probably thought this could be a way to achieve more accurate aggregation with significantly reduced communication costs.
Makes sense.
And they further reasoned, probably, that the reduced number of trainable parameters in their approach would likely be advantageous for privacy-preserving learning by minimizing the impact of added noise.
So they formed a hypothesis.
Yes, and finally, they rigorously tested this hypothesis through all those extensive experiments we discussed across a range of models, tasks, and privacy settings, comparing their results against established baselines to validate the advantages of FedSB.
It sounds like a logical progression of research. Identify a problem, look at existing solutions, find their limitations, and then propose and rigorously test a new approach. So to summarize our deep dive into FedSB, what's the core message for our listeners?
The core message, I think, is that FedSB appears to be a significant advancement in federated fine-tuning. It offers a potentially much more efficient and performant way to collaboratively train large AI models, especially while respecting data privacy. It provides a more direct and, crucially, communication-friendly method for combining learning from distributed sources.
What's the most striking aspect of this research for you, the aha moment?
For me, the most striking aspect is really the elegance and simplicity of achieving exact aggregation by just averaging the small R matrices. It's just a very clever way to bypass the complexities and high communication costs associated with other approaches that aim for similar accuracy in federated learning. It feels neat.
So for you, our listener, who is interested in gaining knowledge efficiently, FedSB represents a more streamlined and effective way to conduct federated learning. This could potentially accelerate the development and deployment of AI models in collaborative and privacy-conscious environments.
Exactly. Which leads us to a final thought for you to consider. Given the rapid progress in artificial intelligence and the growing importance of collaborative, privacy-preserving model development, how might innovative techniques like FedSB reshape the future? How might they change the way we train and leverage these powerful technologies across decentralized systems?
Yeah, what new applications might become viable with such efficient and private methods for distributed learning? That's something to mull over.
Definitely. We encourage you to explore the full research paper and related work to delve deeper into this really exciting area.